Okay, so this is just meant to walk you through Earth's magnetic field. It's kind of a fun, optional, interesting lecture on our Earth. So our Earth, you should remember this from just like, I don't know, sixth grade science. At the center of our Earth is a solid iron core. It's pretty hot in there, 5,700 degrees Celsius. But the strong force of gravity is what causes what usually would be a molten metal to be a solid. But the outer core, it's under less pressure, so it's just basically a churning vat of ionized liquid iron. It's mainly iron, but there's also nickel and some other metals in there. And there's even thoughts that there's lighter elements like silicon and oxygen. But essentially, there's differences in pressure and temperature between the inner core and the mantle, and those differences in pressure cause the liquid to move around in these giant convection currents. And there's also the Coriolis force, which is essentially resulting from, like, as the Earth rotates, it causes other rotation for liquid objects like our water in the outer core, for those materials to kind of move around. So you have these just giant whirlpools inside the outer core. And essentially, you have these ionized iron atoms. So you have these iron atoms that have a charge and they're moving around. And when they move around, they create a magnetic field. And then that magnetic field causes any other charged particles to move because a moving charged particle has its own magnetic field. And if it's in the presence of an external magnetic field, then it's going to move some more. And then those magnetic fields are created and they cause other particles to move, etc. And it's basically this self-churning process that keeps the Earth's magnetic field going. And this process is actually called a geodynamo. And some planets have it and others don't. In terms of the solid planets, Earth has a pretty strong one, but the solid planets don't necessarily often all have a magnetic field. Like Mars doesn't have a magnetic field, but the gas ones do, just because of the fact that they are gaseous planets, and so you naturally have materials that can move around. Okay, so this is kind of a plot that shows the magnetic field of the Earth, and you can see it varies throughout the surface, but essentially our Earth behaves like it's got a giant bar magnet in the middle. So even though there's not this one giant bar magnet inside, collectively the Earth's magnetic field behaves like a bar magnet. It's not necessarily aligned with the geographic poles. You can see it's kind of tilted. Just some interesting things about the magnetic field of the Earth. The geographic North Pole is currently the magnetic South Pole. And when I say it's currently, and that's because there's evidence that the magnetic poles have flipped, and that at one point the magnetic south was the geographic south. The poles actually wander on a daily basis. And right now, there's evidence that shows that the magnetic field is changing quite a bit. And so there's this big speculation of what if the magnetic fields are going to flip soon? But we really don't know that until it happens. And the evidence kind of shows it happens every 250,000 years, give or take 5 to 10,000. So there's no exact way to pinpoint when the magnetic field's going to flip. So if you kind of look at our magnetic field, if we just thought about it in terms of outer space, this is the shape that the magnetic field of our Earth would have in outer space. Notice that the moon is outside the realm of our magnetic field. Our magnetic field isn't very strong. It's about 25 to 65 microteslas at the surface. And then as it goes outward from the Earth, it gets weaker. But it extends pretty far out into space. On its own, it has a really nice pattern. Problem is, it's not on its own. It's in space. The sun has a pretty huge effect on the Earth's magnetic field. It's constantly sending out a stream of charged particles. Collectively, it's called the solar wind. And these particles can have accelerations anywhere from 200 to 1,000 kilometers a second. Now, keep in mind, these are moving charged particles. And so we have learned that if you have a moving charged particle, that is innately going to create a magnetic field. So there is an overall magnetic field that's created by these charged particles, by the solar wind, and it's called the IMF, not the International Monetary Fund. It is called the Interplanetary Magnetic Field. So it is essentially the magnetic field that is permeating the space in our solar system that's caused by these charged particles that are coming off of the sun. And the solar wind, when it hits our magnetic field, it's essentially there's two magnetic fields interacting with each other. And so it really warps the shape and the strength of our magnetic field. So there's a couple different regions you can see here. Let me see if I can get my pen to work. You can see here that the solar wind is like coming and hitting our magnetic field, and it causes like this bending to occur from our magnetic field. And so this outer region here, it's called the magnetosheath. And this is a region where the Earth's magnetic field and the IMF, they're vying for control. There's a lot of magnetic turbulence in this region as some of these particles are being affected by our magnetic field and some are not being affected by our magnetic field. Outside this region, the IMF, the interplanetary magnetic field, isn't really affected by the Earth. Okay, so this is where our Earth is going to begin to deflect some of these particles from the solar wind. So then this region right here, this magnetopause, it's a rather thin region. Well, it's not actually thin in terms of astronomical units, but this is a region where essentially you have these particles that are trying to bombard into our Earth, and when they get bombarded into our Earth, they get reflected back out. And so in this magnetopause is where you have these particles that are being pulled inward here towards the Earth because of gravity, but they're also being pulled outwards because of the magnetic field due to the IMF. And so this is a where there's like a net balance of zero force acting on those particles. Okay, so it's kind of a stable zone there. So you've got the magnetosheath on the outside, where it's kind of this uncontrolled wild west of particles being deflected, etc. You've got this magnetopause, where it's kind of this calm area. There's an equal balance of forces. And then inside here, this is where we kind of think of it being the magnetosphere, or the Earth's magnetic field, after we take into account the solar wind. So here's another visual of this. So this is the magnetosphere inside the region of the magnetosheath. So here's the red line is the magnetopause, okay? And so inside here is our magnetosphere. So inside here, you essentially have particles that are trapped within the Earth's magnetic field. And there's three main regions in this. It's kind of interesting. These regions were kind of they didn't know there were these regions, and when they sent up the very first satellite, I don't even call it a satellite, Space Explorer 1 in 1958, one of the things that they attached to it was essentially a Geiger counter, which ticks when it's near radiation. It's the classic in like sci-fi movies where it's like tick 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 whenever there is like a higher amount of radiation. They essentially had that next to a tape recorder, so the tape recorder was just detecting audio signal. And so the Geiger counter would go tick, 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 tick whenever there was any type of radiation, and the tape recorder would record it. And what they found was when the Explorer was like being launched out into space, so here it is from Earth, gets launched out, it found these regions of tick, 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 and then not so many ticks, and then tick, 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 and then not so many ticks. And then it really calmed down over here. And so it was like, whoa, what is going on? There's all this radiation inside or close to our Earth. And so that is kind of caused by our magnetic field. And so what happens is you have these, we'll call them three different regions, and they kind of bleed into each other. There's no like definitive like borderline between these regions. But essentially these red regions here, those are called the Van Allen belts. And then this blue region here is called the plasmasphere. So the outer Van Allen belt essentially traps high energy particles that originate from the sun. So again, with our solar wind, a lot of the stuff gets deflected off, but some definitely make it through. And so you end up having high energy electrons, and their energy values range from like 0.1 to 10 mega electron volts. And they get stuck here in this region because of the magnetic field from our Earth. And then in the next region, you have charged particles that they're high energy, they're in the plasma state, but they're actually much cooler. They don't have as much energy as what we see here in the outer Van Allen belt. And so it's just called the plasmasphere. And then we have another region of high energy particles. And here, the particles that get trapped here, there are some electrons that are like coming from the solar wind that get trapped here. But with this inner Van Allen belt, what happens is you have these charged particles, they make it through, they actually hit our atmosphere and think they get bounced off. Our atmosphere does a great job of blocking a lot of these particles. And so what happens is when these particles get blocked off, we end up getting some decay happening in that interaction. And so you end up having high energy protons that get stuck here in this lower Van Allen belt. So the outer Van Allen belt traps electrons and this that are from the sun, and the inner Van Allen belt ends up trapping protons that are a result of decaying particles that bounce off or reflect off our atmosphere. Um, the Van Allen belts are mostly intense here around the equatorial regions. You can kind of see they form like these like rings, and there's 3D models that show it's a lot like a donut shape where you have these rings encompassing the Earth, and so they're actually pretty weak here around the poles. And because of that, because they're weak around the poles, we end up getting more radiation or these high energy particles that come in through the poles or into our atmosphere from the poles. And we'll talk about in a moment in terms of what the results of that are. But essentially, the magnetosphere, it's not a constant. It can definitely grow or shrink in size depending on the strength of the solar wind. If it's weak, then the magnetosphere kind of expands out. If it's strong, it compresses the magnetic sphere, and it compresses it over here in this region that's closer to the sun. And sometimes we actually get what are called these coronal mass ejections, or CMEs. And they're essentially these solar flares that burst out from the sun. And when those happen, they really can cause distortion here of the magnetic field. And in fact, it causes a huge distortion. I'll show you a video at the end of this. It causes a pretty huge distortion that actually can cause like almost like a rubber band effect with the magnetic field and how it pinches and then it kind of collapses back on itself. But they're called geomagnetic storms. They can have pretty big consequences. In 2003, there was one that happened on Halloween, and weird people were like, "Oh, it's like, you know, evil spirits that are causing this." But it was actually a pretty big storm, and it damaged actually a third of NASA satellites in the atmosphere because the magnetic shielding wasn't there for these. The largest document storm on record happened in 1859, and they don't have necessarily any quantifiable data in terms of the strength of magnetic field, but they were actually able to see the aurora borealis as low as Hawaii. And so that is a definite visual cue that something's changing with our magnetic field. And our magnetic field, it not only deflects the solar wind, but it also deflects like cosmic rays or high energy particles that are coming from outside of our system. So the last thing I want to talk about, well, let me go back. The last thing I want to talk about is, remember we said that in these regions here, the shielding isn't as good at the poles. And so because of that, you can have charged particles that are not as deflected at the poles. And one of the coolest results of that are the aurora borealis, the northern lights, and there's also the southern lights. But we definitely see the northern lights here more often than we see the southern lights, just because we're not here. Like there's not a landmass. You can go and be like, ooh, pretty. But up here, there's definitely lots of different countries where there's inhabited regions and people have just much better documentation of the northern lights. So in terms of what's happening there, you have particles that are penetrating our ionosphere and our atmosphere. And when they collide with atoms, they give that collision, energy is released, and that energy can be released in the form of light. And so in terms of what causes colors, typically when particles collide with oxygen, you get yellow and green. When they collide with nitrogen, you get red and violet, and occasionally get blue. It also makes a difference in terms of where the collision is happening in the sky. And so it's affected by altitude. So usually if the collision is happening 240 kilometers above the surface of the Earth, we're going to get red. Up to 160, we're going to get green. And then purple, we're going to get 95 and above. And then blue, usually up to 95. So you definitely see more of these blue and purples when you go online and watch videos of this, because a lot of the collisions that the light is able to kind of allow us to see that is going to be in those lower regions. And they can manifest as just like a static band of light. If the solar flares are pretty strong, you can have dancing like waves of it. So it's pretty interesting. Like that's one of my bucket list items, is to go and see the northern lights.
In this visualization, Earth's magnetic field structure is represented by lines that correspond to the paths charged particles would travel close to the Earth. The Sun's magnetic field, carried in the plasma of the solar wind, flows continuously by the Earth, distorting the planet's field and pulling it back into a windsock-type structure. The red illustrates the higher density plasma which forms the magnetopause, the boundary between the magnetic influence of the Sun and the Earth. The wind also forms a lower density magnetotail behind the Earth, represented by blue in this computer model. This process is happening all the time as the solar wind is constantly flowing by the Earth. But a coronal mass ejection, or CME, can change things. The higher density plasma and stronger magnetic field carried within the CME strikes Earth's field and significantly alters the structure. Here we see the dramatic changes in Earth's magnetic field and the shape of the magnetopause as the CME passes Earth. But close to Earth, the magnetic field is largely unchanged. Earth is protected from the intense solar event. This is the case for a rather ordinary CME. In this example, a CME launched by an X3 flare from December 2006. But what would happen in the case of a more intense event, such as the Carrington event of 1859? With the aid of similar computer models as before, we can explore some of these possibilities. Here, a much stronger CME compresses the magnetic field between the Sun and Earth and generates more density in the bow shock, represented by darker red. The front of the magnetopause is pushed much closer to the Earth than usual. Even the field and plasma trailing behind the Earth are more strongly distorted.